Okay, today we're going to start taking some notes on energy. So before we get started, go ahead and download, document conservation of energy diagram notes and practices from our Canvas page or Schoology if you're using Schoology. And you can see we have some reading for you to do. So go ahead and pause the video right now and go ahead and read this whole slide. And while you're reading, pay special attention to the questions: where does the energy we use go? What does it become? And how is energy lost if it can't be destroyed? So go ahead, pause the video now, and go ahead and read this first slide. Okay, so you should have a good idea now, after doing that just quick reading, regarding what the conservation of energy really is. So what we mean by that, when something is conserved, that means it doesn't change, okay? So what we're saying here is that energy can't be created, and it can't be destroyed. It can, however, transfer. So we can move energy around. So energy can move from one object to another. Usually through a process called work. And that's a term we use in every day, but it means something different in physics that we're going to talk about towards the end of this unit. Okay, so energy can move from one object to another, and energy can change forms. And we're going to spend a lot of time talking about the different forms that energy takes. Usually in physics, we're going to restrict our discussion to what we call total mechanical energy. So from chemistry, you're probably familiar with chemical energy, and you studied solar energy, I'm sure, in biology, and you're probably aware of nuclear energy. So there's lots of different types of energy. We're going to mainly deal with mechanical energy, and we use TME to stand for total mechanical energy. And total mechanical energy is made up basically of three types of energy. It's made up of gravitational potential energy, it's made up of kinetic energy, and it's made up of elastic potential energy. Okay, we're going to talk about each one of these in more detail. But let's kind of tie in these first two bullet points together: conservation of energy and total mechanical energy. When energy is conserved, and when we're looking at total mechanical energy, we're going to say that the total mechanical energy initially is equal to the total mechanical energy final. Kind of like this, and I'm going to use a different term here. I need to erase this little guy. Nope, that was a highlighter, making it worse. Let's see if I can get that gone too. Nope, apparently not. Okay, figured it out. I'm going to go ahead and use I, not O, to stand for initial. So the total mechanical energy initial at the beginning of the problem is going to equal the total mechanical energy at the final end of the problem. Now, sometimes we also have to consider thermal energy, because sometimes we lose energy to thermal, but we won't normally have to worry about that. So we'll kind of indicate in the problem if that's something we're going to have to worry about or not, okay? So let's take a look at our first type of energy, gravitational potential energy. So we usually shorten that up, GPE. And we can calculate that because it's solely based on an object's mass, okay, the acceleration due to gravity, and an object's height. So let's talk about these in more detail. So M is just standing for mass here. G is 9.8 meters per second squared, and H stands for height. So think about what that means, gravitational potential energy. If you have two objects at the same height, that means the more massive object has more gravitational potential energy. And if you have two objects of the same mass, that means that the higher object, the one that's higher off the ground, has more gravitational potential energy. And I bet you're not surprised by that, because you can imagine if you have two objects, one not very massive and one very massive, and you drop both on your feet, right? Which one's going to hurt more? Well, the one that's more massive is going to hurt more when it hits your foot, because it has more energy, and it's put a lot of that energy now into breaking your foot. Likewise, if you have two objects that are pretty light, and you have one that's really, really high and one that's not very high, and you drop both on your feet, clearly the one that's higher up is going to injure your foot more than the one that's lower up, okay? Now let's go ahead and talk about some units here as well. So if GPE is mass times G times height, okay, remember G is just 9.8 meters per second squared. Let's take a look at our units. So the units we're going to use for mass is always going to be kilograms. G is going to be meters squared, and height is going to be meters. So we end up with units for GPE of kilogram meters squared per second squared. That's kind of an awkward unit, and as physicists like to do, we gave that a different name. Okay, this is called a joule. So 1 kilogram meter squared per second squared is equal to 1 joule of energy. And notice how it's spelled, Joule. Okay, so we're going to measure, usually, there are other units. This is the SI unit, the metric unit. Okay. There are some other units. You're probably very familiar with calories. Calories is a measure of energy as well. So if you look at the back of any food that you buy, you'll see calories on there, and it's just a measure of how much energy is contained in that food. So obviously that's the kind of energy we eat, and that's where we get our energy. Okay, so we're going to go ahead and use joules. So go ahead and maybe highlight that so you keep that in mind. Okay. All right, now we can talk about kinetic energy, because as an object falls, it loses gravitational potential energy and it's going to gain kinetic energy. And we can calculate kinetic energy as well from an equation 1/2 mv squared. So again, m is going to stand for mass, measured in kilograms, and velocity, v stands for velocity, measured in meters per second. So let's take a look at our units for kinetic energy, see if they match up with gravitational potential energy. They certainly should. We end up with kilogram meter squared per second squared, because that velocity term is squared. So again, we end up with a joule, and that's what we're going to use to measure kinetic energy and potential energy and all energy, as a matter of fact. Okay? Finally, we have elastic potential energy, and this is simply stored energy in something like a rubber band or a spring, okay? Anything that's elastic, okay? Anything that's kind of stretchy can store energy. And it can release that energy then when it goes back to its original size or shape, and then that energy becomes something else. Normally we're going to look at how that energy becomes kinetic energy. So really our key takeaways from this first slide here is that the energy is conserved. That means we can't lose it. It's not created. It's not destroyed. It just turns into something else. And I want to highlight the equations as well. So I would suggest you write these down somewhere where you keep all of your equations. So the main ones are going to be our equation for kinetic energy, our equation for potential energy, and this idea that the initial total mechanical energy has to equal the final total mechanical energy, so we don't lose any. So write those down. Make sure you have access to those whenever you need them. All right, so let's see if we can get a sense of how exactly energy changes from one form to another. So let's take a look at a couple of situations. This first one, we're going to look at a before and we're going to look at an after. So before is kind of over here, the after is over here. And we're going to fill in these charts here with what type of energy we have. And notice how we're starting with our bar chart of total mechanical energy all filled up. So we have to determine, all right, how much of this total mechanical energy is gravitational potential energy and how much of it is kinetic energy, just as a ball is released from some height. So we got our little kid here standing on a chair. I hope he's okay. And he's dropping something. I'm not sure what he's dropping. It looks like it's a ball. Okay, it looks like he has a feather in his other hand, but let's just worry about the ball. Okay. And then we're going to look at what the energy is right as the ball hits the ground. We're not going to worry about what happens once the ground has slowed it down. There's more physics than we want to get into. So let's just worry about the instant the boy lets it go and the instant the ball hits the ground. So when he's holding the ball and just let it go, the ball has not had a chance to speed up. Its velocity is 0. So that means that it can't have any kinetic energy. So all this total mechanical energy must be gravitational potential energy. So we can indicate that simply by coloring in our gravitational potential energy and filling in all those. Now, clearly my kindergarten teacher is not very happy with me right now. I'm colored outside the lines, but I trust that you guys can do better, okay? Now, let's take a look at the after situation when the ball is just about to hit the ground. Realize that the height of the ball at this point is 0. So since our equation for gravitational potential energy is that GPE equals m times g times h, if the height is 0, then there can't be any gravitational potential energy. That means all of this energy that we started with must have become kinetic energy. It can't become anything else. So if you're thinking, well, maybe it's elastic energy, well, we haven't had anything transform. Maybe this is an elastic rubber ball, and maybe it will, but we're not going to worry about that situation right now, okay? So it's not elastic energy. It didn't become chemical or anything weird, right? We're kind of sticking our analysis to gravitational potential energy, kinetic energy, and we're going to bring in some elastic potential energy in a few minutes, okay? So that's our first example. Let's do another example together. So now we have cyclists on a bike coasting toward a hill. Now they're coasting because if they were pedaling, we would be basically adding some energy into the system, and we're not creating it, we're just getting it from the people, and we want to make it a little simpler. So they're not pedaling, they're just coasting. So they're at the bottom of the hill right now, okay? And they're going to go ahead and they're going to get to the top of the hill in a second here. So let me erase, I made some mark here that I don't want. Let's go ahead and see now after they are at the top of the hill, they're going to go ahead and they're going to coast all the way up. Start at the bottom, they're going to coast to the somewhere halfway up the hill, it says. So when we start at a height equals 0. And we're going to find that in order to do these problems, we always have to define where our height equals 0. So let's go ahead and realize that if we're starting at a height of 0, we can't have any gravitational potential energy. So all of that initial energy, that total mechanical energy, must be kinetic. We don't have any gravitational potential energy. But then the same cyclist coasts up to a stop halfway up the hill. So now this is kind of our after. If they're stopped, they can't have any kinetic energy. All of that total mechanical energy must have become gravitational potential energy. Okay. Now these are kind of two pretty simple examples, but I think it gets us started on where we need to go. Let's try a couple more here. Let's look at another one where we've got a roller coaster. And notice that it says the roller coaster is in motion at the top of a hill. So let's assume that we start with a whole bunch of total mechanical energy. I'm going to use my highlighter here. And we start with a full bucket of total mechanical energy. So we've got, 8 bars worth of mechanical energy. Now, since we're at the top of the hill, you would think that most of that energy is going to be gravitational potential energy. And I would agree, but I think we must have at least one bucket of kinetic energy because it's in motion. So if we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 buckets of total energy, and I'm saying, well, maybe one of those is kinetic energy, that means that the other 7 must be gravitational potential energy because it's in motion. Now later on, we're at the same roller coaster in motion at the bottom of a hill at ground level. So if we're at ground level, we're going to assume that the height is 0. So a couple of really important things here. First of all, the total mechanical energy that we have at the bottom has to be the same as what we had at the top. So we can go ahead and we can fill in our total mechanical energy without even doing too much thinking. We know that that has to be the same. And then I look at the problem and I say, well, none of that energy is gravitational potential energy because we're at the bottom. So all of that is now kinetic energy. So now I can go ahead and I can fill in all my kinetic energy. Okay? This next one's a little tougher. We're going to break this into a couple of different parts. So we've got a diver. This does not look safe, by the way. I'm not a fan of this diver here. On top of a cliff in Acapulco. Although I am a fan of Acapulco. So there's no downward velocity yet. So we're going to assume that they're moving a little bit to the left and the right. Okay. So again, let's assume that we've got all the energy we're going to get. Okay. So our total mechanical energy, we're going to shade in all of those 8 boxes. And I'm going to say that some of that is kinetic energy. Right? Because he's hopefully moving away from the cliff. But the rest of it has to all be potential energy. So I'm going to go ahead, put it all as potential energy. Now, when we're halfway down the cliff, we must have lost a lot of that potential energy. We must have lost half of it. So we've got 1, 2, 3, 4, 5, 6, 7 boxes. So I must have lost a bunch. So I've only got 3.5 boxes left. but my total energy is still the same. I've still got all the same total energy. So if I've got 3.5 boxes of gravitational potential energy, I must have 4.5 boxes. 1, 2, 3, 4.5 boxes. Oh, that doesn't look like a half. We'll try it again. Close enough. Of kinetic energy. Now, you could make an argument that he just kind of stepped off of the cliff, and in that case, all of the in this first chart here, all of the total mechanical energy would be gravitational potential, and then over here we would have an even amount of gravitational potential energy and kinetic energy. But I'm hoping that he gave himself a little velocity there. Okay. Now for our last one, again, we still know that the total mechanical energy has not changed. But if he's all the way at the bottom of the cliff, he has no height anymore. So his gravitational potential energy must be 0, and all of that energy must have become kinetic energy. All right, a couple more here. All right, so we're going to bring in elastic potential energy now. And we don't have an equation for elastic potential energy. Sometimes we do. But we won't use that equation in this class because we're not going to be real specific about the type of elastic energy we're storing, okay? So what we've got here is we've got a slingshot. Who doesn't think a slingshot is cool, right? We've got a slingshot, and we've got a water balloon, and it's in the stretched slingshot. And we're going to look at 4 different periods of time. We're going to look at right at the start, before the water balloon is released. We're going to look immediately after the water balloon, the slingshot, is released. It hasn't gained any height, and the rubber band, the slingshot, is no longer stretched. So it's not storing any more elastic energy. Right now, when it's fully stretched, it's storing all the elastic potential energy it can. When it's unstretched, it's not storing any more elastic potential energy. Then we're going to look at what happens at the way top of its arc. So it's the water balloon is as high as it's going to get. And then we're going to look at what happens right as it hits the ground. Okay, so its height is 0. Okay. So when we start out at the start, before release, and we're just going to assume it starts at ground level or close, very close to it. Before release, we know it's not, since the height is 0, we know we don't have any gravitational potential energy. And since the water balloon isn't moving, we don't have any kinetic energy. So all the energy we have must be elastic potential energy. So we can go ahead and shade that, okay? Now, after the balloon is released, after the slingshot is released, okay, immediately after release, but no height, we still don't have any gravitational potential energy. And we know we don't have any elastic potential energy. So all of that elastic potential energy must have become kinetic. So now we know the balloon is moving really fast. It hasn't gone anywhere yet, but it's starting out with a really large velocity, okay? Now at the top of its arc, we know it's at its highest point. So we know we didn't gain any elastic potential energy. That would have been impossible. And we know it's not stopped because it's going at an angle. So we know it's not stopped. So we know we have some kinetic energy, right? But this is the least kinetic energy we're going to have. So maybe we have 2 bars of kinetic energy. Well, that means the rest of the energy must be gravitational potential energy. So maybe 6 bars of gravitational potential energy. Now when it hits the ground, no more height. We know we've lost all the elastic potential energy. We know we've lost all the gravitational potential energy. So all the energy we initially started out with must be kinetic energy. So all the initial elastic potential energy has become elastic potential energy. Sorry, has become kinetic energy. All right, last one. And we're going to deal a lot with roller coasters. Roller coasters are a great example for energy and energy transformation. So we have a roller coaster here, and we're going to consider the energy at 4 different points, A, B, C, and D. And notice we don't have any elastic potential energy because there's no springs or stretchy items going on with the roller coaster. So we're only going to now go back to considering gravitational potential energy and kinetic energy. So the first thing we can do is we can decide, okay, at point A, and really every point after that, our total mechanical energy, we're just going to assume we have 8 bars. So we can go ahead and fill that in right here for part A. And if we assume that the roller coaster is just not moving at point A, so it's basically reached the top of that hill. We'll talk about how it gets there later on in the unit. So reach the top of the hill, and it has really no velocity. But but it's got just a teeny weeny enough of velocity to just make it go over that hill, we know that that total mechanical energy must be gravitational potential energy, no kinetic energy, or not enough to even put in a bar. And then at point B, we know we still have the same amount of total mechanical energy. Remember, energy can't be created or destroyed, so we're still the same amount. But now we have no potential energy at point B because the height is 0. So all of that initial potential energy has become kinetic energy at point B. But the roller coaster keeps moving from point B to point C. We know at point C we still have the same amount of total mechanical energy. We can't lose it. Okay. But now only some of it is kinetic, so the roller coaster is slowed down. The higher the roller coaster gets, the more kinetic energy it loses and the more gravitational potential energy it gains. So maybe at point C we have, I don't know, maybe we have 2 bars of kinetic energy, or maybe 3. Let's put 3. And that means we have 5 bars of gravitational potential energy. And when we get to point D, again, the total mechanical energy has not changed, so we can fill that in. But point D is lower than point C. That means we must have lost some gravitational potential energy. So now maybe we only have 4 gravitational potential energy bars. And that means we must have 4 kinetic energy bars as well. All right, so that is it for the notes today. If I went too fast for any of this, feel free to go ahead and rewind this and take another look. Otherwise, we will talk about some more of this in class when I see you next time. Have a great day.